I've talked about mass as the amount of matter, the amount of matter in an object. But the amount of matter is something really quite vague, right? If we imagine any object, a stone or favorite ball again, can imagine holding on to this object or breaking it into pieces. So there are these little bits, or that there's this material that we can hold and touch, and there are stuff inside, right? So this is some kind of a matter. So matter as in whatever stuff we have inside the body, right? It's a very vague idea, but there are some ways in which mass has an effect that we can observe, and we have already seen, as an example, what happens when this body is, say, either at rest or moving with a certain velocity, right, a certain speed, in a certain direction. Okay, so unless well, we might imagine that this is either in outer space or in a perfectly smooth floor. So unless there is some force to stop it or to kick it to another into another direction, it's just going to go straight. Okay, so the mass of this ball has a tendency to resist anything that tries to change its velocity or its speed or direction. Okay, right? If you want to change the speed or direction, you have to apply a force. Otherwise, it will just keep going. So we have seen that. Now, we think of that as an effect that mass has, and the name for this was inertia. Right? I talked about how inertia is a tendency to resist changes to its motion. Now, mass has another very obvious effect that we can see in everyday life, and that is weight. Okay, we all know what weight is. Okay, we all have weights, and we have to work against our weights. And whenever we lift something, there is weight. So basically, these are the two effects. You can think of these two as the effects that mass has. Right, the two effects that we can actually observe and actually measure in some ways. So the both effects can be quite obvious. All right, and weight maybe is the most obvious, because we carry our own weight, we walk, we get tired. Now, if I think of the ball, a little ball here, if you think of the weight, let's think about how weight happens. Now, clearly, weight on an object, the weight on an object means that, if I have an object like that, means that if you drop it, it will fall down, or if you want to lift it up, you need a force. Okay, you need to exert yourself to lift up an object. So the weight is a force that pulls it down, and the force comes from the earth in this case. So let's say this is the ground level. So the force comes from the earth. Now we'll learn later on from about when we learn about gravitation, that these weights that we are so familiar with is actually part of something that happens all the time when we are between two objects that have mass. So in this case, I have let's see, my objects here is this one, the ball here, and the earth here. It is not always obvious that earth is an object or body, because to us it's the ground, right? It's the ground that we stand on. But if we imagine going into outer space, right, we have seen probably seen pictures of the earth as a planet. So if I imagine, okay, let me imagine this. Let me imagine that we zoom out, zoom in, zoom out, zoom out. Yeah, let me imagine zooming out to from outer space, from this ball ground picture. So that would be the earth. All right, let's say that's the earth, and that's the ball. Okay, that's the ball. Okay, earth and ball. So this I've zoomed out, and this is what I see in outer space. Now from outer space, we can see that there are these two objects, and actually, as long as there are two objects that have mass, they will attract each other, right? Earth would attract the ball, okay, downwards, and the ball would also attract the earth. Right? It's a bit hard to imagine the ball attracting the earth. Right? The earth is huge, it's massive, and it has this gravitational force that pulls on the ball. It's hard to imagine that the ball also attracts on the earth. But actually, according to Newton's third law, the two forces are equal and opposite. Let's say the earth pulls the ball down with a certain weight. Okay, so according to Newton's third law, the ball actually also pulls the earth up with the same with a force of the same size, right? With the same weight. That is equal to its own weight. So they pull at each other. Okay, but it's just that we never notice the pull from the earth, for the simple reason that the earth hardly moves when the ball pulls at it. Okay, the ball has a very small mass, so under its own weight, when the earth pulls at it, the ball obviously falls, and we can see the ball dropping. But at the same time, although the ball pulls on the earth, because the earth is so massive, in theory, the earth will also move up a little bit. Okay, when the ball falls down, the earth would also move up a little bit, but that little bit might be just maybe 1 micrometer or even 1 nanometer, just an extremely tiny amount that we'll never notice because of its huge mass. So but just because we never notice it doesn't mean that it's not there. All right, actually there is such a force, and this kind of force between two bodies only become obvious when we talk about gravitational pull between, say, planets, or between Earth and the Sun. Right? If you think of the Earth moving around the Sun in space. So anyway, in this case, what we have just seen is that weights, which is actually gravity or gravitational force. So that's a more basic name for weight, if you like, a name that tells us a bit more about how weight comes about. All right, weight comes about because of attraction between two masses, and weight is something which we know that we can easily measure. right? You can stand on a weighing scale and see your own weight. So the weighing scale might be, say, might contain some spring inside that gets compressed when you stand on it. So when the spring moves, right, it's attached to a scale, or these days a digital meter from which you can read your own weight.